So now that we have some idea of what a process is, let's take a look at the concept of process scheduling. So our issue is this, right? We have a system, right? The system has, multiple processes running out, right? You have different programs doing different things. How do we deal with the fact that we have kind of some, shared resource pool of things, right, that are available, and kind of, scheduling it out, right, or giving it out to those different processes? So we need to take a look at that. So we have this general idea, right, of scheduling queues. The idea is there's some queue, right, or some pool of things that need to get done, right? So I have sort of this queue of all these different processes that want to run. So on the right-hand side, we have basically a diagram of a system, right? So this is basically a queuing diagram. And there's a couple different elements in there, right? So we have these rectangles and we have these circles. So these rectangles, what these are representing, right, are basically queues. So I have over here, for example, this thing called a ready queue, right? I also have my queues over here, right? I have something called an IO queue, right? Time slice queue, fork queue. I have all these different queues going on. So what that's basically saying is each of those somehow are these little pool of resources that need to do something, or a pool of processes that need to do something. The most obvious one is this one up top called the ready queue. So what the ready queue is it's a specific name for a queue that contains processes that want CPU time, right? So a CPU basically is your number one resource, right? So one thing you're kind of parsing out to everybody, right? Everybody wants CPU time, right? Everybody wants to do stuff. We can only have a certain number of CPUs though, and so we have to kind of make them take turns, right? So they'll all sit here in the ready queue, right? Ready queue again is processes that want to run. And now in our diagram, the other notation we have here, right, is of these circles, right? So here we over here we have CPU. So what that's representing is a resource, right? So what we're saying here is, oh hey, I have maybe processes, right, that are sitting in my ready queue, and they're going to at some point, I'm going to draw a little dot here, represent a process. At some point they're going to be pulled out, right, and they're going to be sent over to the CPU, right? So they're actually going to be granted access to that resource, and that means they can actually do stuff, right? So they do some computation, they can run for a little while, right? And so that's kind of the overall, that's kind of the notation behind this diagram, right? These squares, right? These rectangles are representing queues, and these circles are representing resources. And so you can see now, right, in our diagram, as you can imagine, right, I have my process, right? My process somehow, comes out of this ready queue, goes to the CPU, spends some time there, right? There are some places you can go afterwards, right? There's, some choices to be made, right? Maybe that process is done, right? Maybe we've used up all our CPU time, right? Maybe the program is completed, right? In which case you have the arrow going to the right to represent, oh, hey, kick this thing out of the system. It doesn't need to do anything else. The alternative is it may end up in one of these other queues down here, right? And I have 4 more queues that it could possibly go to. And so these queues are basically, is my process waiting to do something? So the kind of the most iconic one or the classic one is the first one there, which is IO, right? So say I have my program running, right, does some computation, does some number crunching, and all of a sudden, right, I need to get the contents of a file. Well, if I need to get the contents of the file, what that means is I'm going to need to go and touch a physical device, probably a hard drive, and be like, oh, hey, I need this piece of data. Well, the problem is your device isn't going to be able to return to you that piece of data immediately, right? Because if you're on something like a mechanical drive, it's going to take a little bit of time for you to basically spin up, right, move your little parts around, right, to the mechanical device. And so because of that, actually what happens is, your I/O device typically has some sort of a queue, right? A queue of, things they need to do, right? So a hard drive might have, somewhere on it, right? Basically it has its own queue, right? Of, I want to read this file, this file, and this file, and this file. And so when your program makes a request, really it has to basically move itself into a queue that's associated with that bit of hardware, right? With that I/O device, right? Because we need to wait for that I/O device to get that piece of information before the program can continue. And so that's what this top part of the diagram, or this middle top part of the diagram where I'm showing, right, is that our program, right, did some CPU time, and all of a sudden, right, it needs to do an I/O request, right, and so it's going to wait, to make the I/O request, right, it's going to go in the I/O queue, right, and eventually, right, once it's kind of its turn, right, because again, right, I have only a fixed number of I/O devices, once it has its time comes up, right, then my process can go, right, and it can jump on that I/O device, right, and it can do something, right, so I can go over here, right, all of a sudden my process is sitting here, it can go and, read whatever it wants, right, and it gets returned back. And then the program can deal with it. Now at this point in time, right, one thing we want to be certain we understand is that there are kind of these different queues my processes live in, right? So even though my process, right, had some CPU time and then went and started doing I/O now, right, even if its I/O request has been answered, right, even if it has, that file information it wanted, it can't just jump right onto the CPU again, right? Because really, sometime in the background, right, well, not necessarily in the background, but sometime in parallel, there would have been somebody else who was allowed to go and work on the CPU, right? Because I have these 2 different resources. I have a CPU versus I have my I/O device. Ideally, I want to have somebody working on those, independently and at the same time. I don't want to just do one at a time, right? I don't want to leave that CPU idle, right? If somebody needs to do some I/O stuff, I should go and let them do the I/O stuff at the same time that another process is running on the CPU and getting stuff done. I don't want anything to ever idle if I can. And so what happens, right, is after I'm done with that I/O device, right, doing my read, I have to return back to the ready queue, right? So again, the ready queue is all the processes that want to execute on the CPU. And so my process will now have to wait its turn, right? I'll have to wait, and eventually, right, that particular process will be picked out of the ready queue, right, and it'll go to the CPU and it'll get CPU time again, and it'll get to do something again, right? It'll do some computation now, maybe with the results of that file, right? And so it forms a little bit of a cycle. And eventually you'll probably, you've done all you need to do, right? And so you can be pulled off of the CPU, right? You can kind of leave, right? And then, you're kind of freed up from this diagram. Now, in the bottom part, right, we have some different routes as well, right? So instead of doing file I/O, right, maybe there's an issue. Well, here we'll talk about this one in a few minutes. This says time slice expired. That's like the idea of, well, hey, maybe I have some process that doesn't need I/O, right? It's just working. And if it's just doing all this work, right, maybe at some point we need to kind of make it pause for a little bit, right? Because somebody else needs to go. We don't want one process hogging up everything. That's all the CPU resources available, right? So we'll say, oh, your time slice, right, the amount of time you're allocated, right, that is, we've exceeded it, and so I'm going to force you to go back in the ready queue. I'm going to take somebody else out of the queue and let them work instead. Again, we'll go into that in kind of a lot more detail later on in the course. The other ones here, right, fork or child, wait for interrupt. Well, those now are kind of operations that a process could perform that maybe entail some sort of resource management, right? We need to wait around for something to be available, or we need to request something, right? Those are going to be actions, right? I'll talk about them a little bit more later, where basically our process, right, needs to sit around and wait for something to occur, right? And after these special operations, like for example, forking has occurred, then you can go back to the ready queue, then you can go back to doing stuff. Okay. So one bit more terminology I should have mentioned here, right, is in addition to the ready queue, right, which is this thing up here, right, which is basically for all the processes that want to go to the CPU. I also have these as my device queues, right. So these over here, which I should try to. So let's see. I want all these 5 basically over here, right. These are all device queues. Well, I don't know if it may not be technically proper to say all device queues, right? But they're basically queues, right? They want to touch some sort of a hardware, right? There's something that they have to wait for, right? Some unique resource that they're queued for. So for now, we'll just call those all device resources. Okay, and then one last final piece of terminology is that when I have a process that's in the ready queue and it's going to the CPU, we say that process is being dispatched, right? So we're going to send it off, right? And this one I can actually do stuff, right? So we'll call that a dispatch. So let's talk about the little highlight at the bottom right now. So I have that in red, right? It says, oh, hey, would it be appropriate to use a priority queue? And so this is actually going back to 222, right? And so a priority queue, right, is something that you guys have probably seen in that class, or almost certainly have seen in that class. Whether you remember it may be a different thing. But the idea of a priority queue, right? I'll refresh you guys a little bit before we talk about the answer here to this question, right? Which is, hey, would it be appropriate to use a priority queue for these queues? Priority queue, right, is basically this queuing data structure where instead of things being kind of stored in order, right, instead of basically going first in, first out, we have basically a value associated with each element in my queue that says, okay, this is the priority associated with it, right? And then when I go to take stuff out of that priority queue, right, I'm going to take stuff out based on that value, right, based on the priority that is assigned to it. Right, so rather than it being specifically to the rather than it being linked specifically to the order rather than it being linked specifically to the order in which I add things, it's linked to the priorities associated with them, right, via a little tag on there. A little bit different than a normal queue. And so you can maybe think about this for 1 second. Would it be appropriate, to use a priority queue to model these queues or not? So this is actually a little bit complicated. And so there are maybe a couple of issues that would maybe come up, right, if we were trying to use priority queues. One of them, which is kind of very significant, is this idea of starvation. One problem is when you have kind of priority in a system, well, if you keep on adding things that are very high priority, those are things that maybe will always be allowed to go first, right? And so maybe I have some things with like a lower priority, they kind of get stuck in the back, right? And if I add newer, higher priority things, after them, well, what happens is, I just never get to those things in the back, right? So that'd be a little bit problematic. The other thing, right, and this is maybe a system design thing, is that priority queues kind of are designed for the situation where priority of the elements never changes, right? You can go back and you can look at maybe the idea, right, of using a heap to store data inside of a priority queue. Basically, one of the assumptions about that, using that method to, or that technique to store data, is that you're never going to change your priority kind of in the middle of the priority queue, right? You're allowed to maybe, to label things when they come in, right, and then you can take things out, but you're not allowed to go in there, right, and tinker with it and change the priority of something that's already there. Because if you do that, all of a sudden you get that priority queues, heap inside of it, right? It's binary heap. That thing goes out of order, right? And I can no longer find what is the maximum. I can no longer find what is the minimum, right? And here it would be nice, right, to occasionally support things like the user saying, oh, hey, this process needs a higher priority, so can you boost it up? And a priority queue, kind of the classical version of it, right, won't support that operation, right? It doesn't support changing the priority kind of in the middle of things. So overall, right, there is some issues with priority queue. with the kind of generic priority queue data structure, and so maybe we want to look at using something else to store these things. So we have these two basically classes of programs, right? Programs that are either I/O bound or programs that are CPU bound. And so somehow the concern for us, right, is because we have programs that act these different ways, we want to know how we can, maybe schedule them somehow, right? We want to have maybe a mix of these, right? If we have all I/O bound, maybe that's a problem. If it's all CPU bound, maybe that's a problem as well. And you can maybe think about that for a second. So if we have maybe some processes running, right? So maybe I have, a couple of processes here, right? Let me do actually like 3 of them, right? So let's say I have 3 in this ready queue here. And you can imagine for a second, right? And we're going to actually kind of implicitly answer that third bullet point there, right? What kind of ratio do we want? You can imagine we have 3 processes there, right, sitting in a ready queue, right? And let's say they're all CPU bound. Well, what happens is I'm running my system, right? I pull something out of ready queue, right? Move it over into CPU, right? Okay, that's fine. I get some CPU time, right? And then maybe it goes, right? It has to, eventually, right? Maybe it has to do some file I/O, or maybe it runs out of its time slice, right? It gets pulled off the CPU, and then somebody else goes there. And that process repeats. Well, what happens somehow, right, is in that pattern, right, is that I will have processes, right, that are basically sitting on CPU here, right, they're doing stuff, but there won't be anybody over here, right? So I/O is another resource, right? It's somebody queued up to read from the hard drive. But even this diagram that I've drawn right now, right, with these little dots, I don't have any dot next to I/O, right? So what I'm showing there is I'm using CPU time, but at the same time I actually have an idle resource, right? So my CPU is maxed, but my I/O device is just there waiting. And so if you have basically a bunch of processes that are CPU bound, that's the pattern you'll get, right? So I'll sit on the CPU for a while, right? And then maybe I have to, get pulled off, I get preempted, right? And I go to the I/O device because I need one read, but maybe it's a really short read, right? So I get done really quick, and go back to the ready queue, right? Meanwhile, somebody else's new is on the CPU, and they're going to sit there for a little while, right? And so that CPU, I end up working at 100% of the time, but whenever my processes get pulled off of it, they only send I/O for a little bit, and so that I/O device for the most part ends up being idle, right? And so that would be not really optimal use of my resources. And you can maybe think of the opposite happening, right? So I can have a bunch of processes in my ready queue, and then if they're all I/O bound, what happens is they go to the CPU for a little bit, they do a little bit of computation, they get pulled off, and they go to the queue for the I/O device. Well, in that case, right, my I/O device queue will kind of, become, all saturated, right, with all these different processes, right? All of a sudden I have a bunch of things here, and there won't really be, that much, running on the CPU, right? Because they're all just waiting for that I/O device, right? They're all queued up for it. And so if I go in either direction, right, all CPU bound or all I/O bound, what happens is basically I'm going to maximize one of my 2 resources, right? So I'm maximizing the use of CPU or I'm maximizing the use of my I/O device. But I have 2 resources here, right? And if I have 2 resources, really I'd like to saturate both, right? I don't want to have just one being kind of active. And so really what we want, right, is so what we want, right, basically is a mix of these 2 things, right? I/O bound and CPU bound. Now the ratio here, right, is maybe a little bit awkward to quantify because it depends, how I/O bound or how CPU bound a particular program is, right? How much time does it need to spend on one of those resources? Ideally, what I want, right, is I want some ratio of these programs, right, that are CPU bound versus I/O bound, such that my 2 devices, right, are always being used, right? So I always have something, that's on I/O, right? I always have something that's using CPU. I don't want to be in a situation where I just have one of these being used, right? I want them both to be used in parallel, right? So whatever mix of processes, I have, that's the behavior that I want, right? And so maybe just as a ballpark, you say, maybe 50-50, right? Or maybe a little bit more CPU, because I/O typically will take a little bit longer than CPU. The point is, right, we want both those resources to be used. Now, the other thing that's kind of, the other thing to discuss here is basically this little component has been added up top. So we have here basically a new part of our image, right? This bit over here. So this is something, again, we'll be talking about in more detail. But what this is basically is a swap type system. So the thought is this, right? Normally I have many processes running on my computer, right? If you go and you open up Task Manager, or you do top, right, in your operating system, right, you'll see a bunch of different things running. And sometimes, right, you have more things running there, right, than really have a shot to run at any given time, right? Not only do you not have enough CPUs for them, right, but maybe it's like, well, I have 10,000 things that need to run. They're probably not going to all run in the next hour or so, right? They're going to be around for a little while, right? Maybe I have tasks that are going to be, waiting for something else key to happen first. I don't know. Point is, right, I have kind of too many things to deal with. Because of that, we have basically the idea of extending our scheduler, right, to support the mechanism of swapping. The idea of swapping is basically to say, okay, hey, some of the processes I have in memory, I'm not going to need them for a while. And so what I can do is I can move them out. I can move them out of my RAM, right? RAM is precious, it's a limited resource, right? I can move them maybe to a hard drive. Then later on, when I need them, I can call them back. And so we'll call this process swapping, where I'm moving from basically my main RAM memory to a storage device, right? Something like a hard drive. This is what we call kind of medium-term scheduling, right? So it's like, well, I know I'm not going to need to run this process for a few hours, so I'll move it out, right? So it's kind of stuff that, I'm doing somehow this scheduling, right? Picking who gets to run, but I'm doing it maybe in terms of a few hours, right? I know I'm not going to do this for a while, so I can, move it out. Now, though, there's actually kind of two other types of schedules on top of that, right? So we actually have also this idea of a short-term scheduler. Short-term scheduler is really what we've already been talking about. That's somehow the piece of logic or the piece of code that looks at our ready queue and picks who gets to go next, right? And there's some kind of metrics behind the scenes. Again, that's something we'll go into a lot of depth later on. But again, right, the idea is these are things that are going to be running relatively soon, and so I want to schedule them right now, right? I want to do that. I want to basically, pick out, who is the next person to run, right, and do that again and again and again, right? This is kind of short-term. So that's kind of the type of scheduler we've already looked at. The last type of scheduler that's listed there, right, is a long-term scheduler. So long-term scheduler, right, typically what this is, right, is it's going to be, for maybe a program or operating system that's going to schedule things in terms of, weeks or months or years, whatever. Years is maybe a little bit much. The point is it's kind of a very, very long term. And so where you see this is maybe it's something like a server, right? So sometimes you may have a server and the server is accepting queries from people. It's like, well, this user wants to do this, and this user wants to do this, this user wants to do this. And these are maybe long-running jobs, right? So maybe something that takes like a week to run. Well, that would be kind of the job of a long-term scheduler to figure out, right? You'd have all these users submitting jobs and all these different jobs. Right, we'll have to basically figure out, what order do we want to run them in, right? Maybe some users have priority over other ones, right? Maybe we want to do shorter jobs first, some other kind of rule that's we need to follow. Now, all these different kind of long-term tasks, right? I'll schedule them, right, and I'll schedule them via this long-term scheduler, right? So we have these three different kind of classes of schedulers. So I have my short-term, my ready queue, right? My swapping, which is going back and forth with the hard drive, and then my long-term, which is something that's typically like a bunch of jobs from users. How do I schedule them over the weekend? That type of thing. Now, some additional terminology here. When we basically take a process out of the ready queue and put on the CPU, what we say is that a context switch is occurring, right? I'm switching to a new context, right? Now that process's context is active, right? So that's one term. The other two terms there, right, just really briefly, right, say that when we run a process, right, we're restoring its context, right? We're restoring that process control block, right? We're taking its state that was maybe saved out, restoring to the CPU, right? Keyword there is restore. When we're done with it, right, then we want to save that state, right? We want to take it, right, and move it back to some, piece of memory somewhere, right? So we'll call that a save, right? So we're saving and restoring the context of these programs as we're moving them from the queues, right, to a particular resource.